Hello everyone, hope you are doing well. Welcome to the online platform Civil Technobricks. Guys, here we will tune for the instantaneous decoding of conceptual knowledge in the field of civil engineering, where study elaborates decoding the earth to build a better world. Today we will go through the core concepts related to the applied engineering geology in the view of civil engineering. Engineering geology integrates geological sciences with engineering applications to understand subsurface conditions. So basically, engineering geology, which consists of geological sciences, engineering mechanics, and environmental context. So engineering geological sciences are the structure, minerals, and tectonic processes, where engineering mechanics includes stress, strain, and load distribution, followed by the environmental context where the pore water pressure, time, and confining pressure is introduced. The application of geological sciences to engineering study, which ensures that geological factors which are affecting location, design, construction, and maintenance are recognized and calculated for the sustainable infrastructure development. Geological factors such as rock type, mineral structures, and groundwater are directly influence on the engineering projects. So engineering mechanics and environmental conditions must be evaluated along with geological characteristics. Geological investigations helps us to identify that the construction challenges before any project construction and its execution phase. So applied engineering geology ensures that the safety, economy, and sustainable infrastructure development in coming future. Owing towards the scope of engineering geology, site selection, site exploration, material sourcing, hazard mitigation, design optimization, these are the various domains which are more important to be focused. So site exploration helps to determine subsurface geological condition before construction, like mapping of bedrock, identifying fault zones, and evaluating groundwater depth. Second, material sourcing, which identifies the suitable rocks, aggregates, and soil for engineering works, where these parameters are most important to check on the basis of compressive strength. Third one, that is the hazard mitigation, where the prediction and engineering applications of, or we can say that the prevention and mitigation techniques for landslides, seismic vulnerabilities, and subsidence are more important. Fourth one, the design optimization uses geological data to improve structural safety and economy. So determining safe foundation depths, tunnel routing, and slope angles based on the rock mechanics, which is most important. So the scope of civil engineering point of view, engineering geology supports all stages of planning, design, construction, and execution. The relationship between the geology and the civil engineering, that is the symbiotic workflow, which shows that relationship of geology output with reference to the civil engineering action. Three phases based on the ground condition, the excavation position, and the environmental condition. The ground condition, where massive quartzite has a compressive strength of greater than 1800 kg per centimeter square. That type of foundation or that type of ground is most important in civil engineering action for to design the load bearing size and type of or selection of the foundation. Second one, the excavation, which identifies orientation and spacing of rock joints. For civil engineering domain, it calculates the safe cut angle for highway slope design. Third one, the environment, that will be useful for calculating the high pore water pressure in the substrate or in the atmosphere with reference to the civil engineering application, that is designs specialized drainage and adjust hydrostatic load calculations. Here the geological information directly influences engineering decisions, where the rock strength determines foundation and structural design requirements. So the relationship between geology and civil engineering, which is most important parameter for excavation point of view also. Excavation methods depends on rock mass characteristics and discontinuities in it. Groundwater conditions influences drainage systems and hydraulic structures. Geological observations are converted into engineering solutions during project planning. For the role of engineering geologist, for each and every project there are four phases that each and every engineering geologist must have to be focused: from pre-feasibility to site investigation, then design phase, and at the end construction phase. So before starting any type of construction projects, the role of engineering geologist is most important. That engineering geologists participate from project feasibility studies to construction stages. During site investigation, they assess rock formations, faults, geological strata, groundwater conditions, and subsurface explorations. That is phase 1 pre-feasibility, where desk studies are carried out by using some remote sensing techniques and aerial photogrammetry analyzed by that engineering geologist to spot the regional fault lines. Second phase will be the site investigation, where the surface mapping, core drilling, and geophysical surveys are carried out by the method of seismic activity or elastic wave velocities, where the geological data supports the designs decisions for foundation, dams, tunnels, and highways. During construction point of view, the geological monitoring helps identify unexpected subsurface conditions. Before that, the design phase is most important for the rock mass point of view, which provide the rock mass classification, permeability rates, fundamental strength data, and structural engineers activity, so that the each and every design must suitable for that strata which is available beneath it. And the last phase is related to that construction activity, which is the on-site monitoring, which verify and predict the rock conditions which are available based on some geological characteristics against the actual excavation and monitoring joint stability. Here, the role of engineering geologist most important to study the existing rock surface beneath to that construction activity which will be proposed, and the whole geological subsurface and its investigation criteria is designed according to that project, just like dam, tunnel, etc. So continuous geological assessment which minimizes the risk and failures in coming future. Geological investigation before construction. Here, the three levels of the strata are defined: that surface level, shallow subsurface, and deep subsurface. Surface level is at the topmost level, where shallow subsurface is the middle one, and third surface at the bottom, that is deep subsurface. So, surface level, which includes the aerial or satellite mapping, which identifies regional fault lines, crest topography, and large scale joint patterns. This surface investigation includes geological mapping and remote observations basically. Second one will be the shallow subsurface, that is geophysical methods, where seismic and gravimetric analysis is carried out. Seismic analysis includes that the measurement of elastic waves by using the P wave velocity. For example, solid granite transmits at 13,000 to 25,000 feet per second, which lose alluvium at only 1,900 to 6,400 feet per second. Likewise, the whole study of rocks on the basis of wave velocity is carried out. Second one will be the gravimetric analysis, which detects the dense ore bodies or subsurface voids which are present beneath to that surface level. That shallow surface investigates uses of trenches, pits, and geophysical surveys. Third one, the deep subsurface, that is the actual core drilling, where the external factors are in picture, which extracts physical rock samples to test the rock quality, designation, and verifying the stratigraphy. That deep investigation involves drilling, bore holes, and core logging. Here, the geological investigations provide information about quality of rock, groundwater conditions, and many more. These studies reduces uncertainty and improves engineering decision making. Most important factor, that is the environmental point of view. That environment factors altering the rock strength. So there are four factors that factors affects the strength of rock, because for the foundation of any structure, the strength or the compressive strength, which is most important factor to study. First factor is the confining pressure, which is acting vertically downward, which affects that existing strata, which refers to the ultimate strength. Rock that are brittle at the surface become plastic, and which deform continuously at the depth. So confining pressure significantly affects rock strata continuously. Second factor will be the time or creep, which causes slow continuous deformation below the elastic limit over long periods. Then temperature changes may alter rock properties and stability also. Third one will be the pore water pressure, where The high fluid pressure partially balances lithostatic pressure or topographical conditions, effectively decreasing the rock strength and cohesion, where water pressure reduces effective stress also and weakens the rock masses or the rock layers or tectonic plates. Fourth one will be the anisotropy, where weathering gradually decreases rock strength over time. The strength varies by direction. A rock compresses parallel to its foliation, which is much stronger than one compressed perpendicular to it. So the factors which are acting on vertically downward or vertically upward at the same time, anisotropy, these are all the factors which are acting the stresses or forces obliquely at the same tectonic plates, and that whole factors impacting, and the all factors which are most important to consider while starting the actual execution of project. So the graphical representation explains the confining pressure on the x-axis, whereas ductility in percentage on y-axis. The all graphs showing that at the initial level where confining pressure is goes on increasing, at the same time the ductility is also goes on increasing. We define each and every rock and its process of environmental impact on that type of rocks, or we can say that the ways of rock strength. Stay tuned guys, happy learning.